Alright, in this lecture we're going to take a look at pure bending of a prismatic beam using the semi-inverse method. So this would be a three-dimensional elasticity problem. We're going to look at isotropic materials, pure bending, prismatic. What that means is the cross-section stays constant throughout the length of the beam. Despite what my picture looks like, it's supposed to be a constant cross-section beam. And the coordinate system I'm going to use is z going down the axis, x going down, and y going to the left as we look down the end of the beam. We will need the moment of inertia of the cross-section, 1/12 the base times the height cubed, and we'll introduce that at a little bit later time. Well, from elementary mechanics of materials, we have an idea of what we would expect the stress field to be. Now remember, this is going down the z-axis. We would expect the stress to get higher on the bottom and top edges, and it changed linearly from the distance from the centroid or the neutral axis. So the assumed stress field that we're going to use for the semi-inverse method is sigma z is equal to minus mx over I. Now, a lot of books take the x-axis to go down the length of the beam and the y-axis to go up the beam, and so you may be more familiar with this equation as minus my over I. It's the same equation, we're just rotating our coordinate system in a little bit funny of a way. Alright, now we are going to neglect body forces. And in that case, we will have equilibrium apply. So remember, our equilibrium equations are sigma ij comma j is equal to 0. The third of our equilibrium equations looks something like this. The partial of tau xz with respect to x plus the partial of tau yz with respect to y plus the partial of sigma z with respect to z plus the body force in the z direction is equal to 0. Now if we neglect this body force, and we notice that when we take the partial derivative of minus mx over I, we get 0. All the other stress is 0. Then our equilibrium equation is satisfied, and so are the other two, because all the other terms have vanished. Alright, we can look at strain displacement. For small strains, epsilon ij is equal to 1/2 partial of ui with respect to xj plus the partial of uj with respect to xi. And we can look at compatibility. So let's see if I can write this down. Epsilon, had it written down on the previous page, ij with respect to x m and xn plus second partial plus the second partial of epsilon mn with respect to xi and xj is equal to the second partial derivative of epsilon im with respect to x j and xn plus the second partial derivative of epsilon jn with respect to x I and xm. And I don't write that one down all that frequently, so let me just take a moment and make sure that I haven't made any mistake in there. And that was indeed correct. And notice those are second partial derivatives of the strains with respect to position. And our stress-strain relations say that at most our strains are going to be some constant times the stresses, and so by the time we take the second partial derivatives with respect to x, all of those terms will vanish as well. So compatibility in this case is also satisfied without having to worry about enforcing that in some other way with our equations. Alright, so what we really want to do now is we want to investigate what our displacement fields are for this particular beam. So we're going to work with our strain displacement, and then we'll come up with a set of partial differential equations to integrate for those displacements. Let's make a little bit of room. Alright. So our stress-strain relations, since this is a uniaxial stress state, we're assuming we're just going to use the traditional modulus of elasticity E and Poisson's ratio. So epsilon x is going to be equal to sigma x over E, and epsilon z is going to be equal to sigma z over E. Epsilon x and epsilon y, the strains will both be equal to minus nu sigma z over E. Now strain displacement tells us that, let's write them over here, I guess, partial of, epsilon x is equal to the partial of u with respect to x. Epsilon y is equal to the partial of v with respect to y. Epsilon z is equal to the partial of w with respect to z. If we look at our engineering shearing strains, let's write them over here. Engineering shearing strain gamma xy, it's going to be twice the tensor shearing strain. It's going to be equal to partial of u with respect to y plus the partial of v with respect to x. Gamma xz is the partial of u with respect to z plus the partial of w with respect to x. Gamma yz is equal to the partial derivative of v with respect to z plus the partial derivative of w with respect to y. And in this particular case, all three of these shearing strains in this coordinate system are going to be equal to 0 for a state of stress of pure bending. And at this point, I'm going to go ahead and label these equations so we can kind of keep track of them. Call it A, B, and C, and D, E, and F. We will have some occasion to get back to those. Now, just like all the other examples we've done with partial differential equations, this gets to be a little bit of a puzzle. So let's start with equation C, which is for epsilon z. It's equal to the partial derivative of w with respect to z, and based on our stress-strain relations is equal to minus m x over IE, or EI. So if we want to integrate this, we would integrate this with respect to z. We would get w equal to minus m x z over EI. Now when we're integrating with respect to z, we could potentially have thrown out a function that is a function of x and y. And we can include the constant in here, or we could not worry about it. The constant, again, will just represent rigid body displacement of the entire beam. In most practical circumstances we can think of, the beam being fixed for some reference frame that we have, and everything else being with a rigid motions taken out of it. So we're not going to worry too much about any strict constant of integration that we might have. At least not at this point. So then let's take a look at the partial derivative of this with respect to x. We'll see where we'll use that in here in just a moment. The partial derivative of this with respect to x is a minus mz over ei plus the partial derivative of f1, which is a function of x and y, with respect to x. Now what we're going to do is we're going to use that in equation E. Now, equation E says that the partial derivative of u with respect to z is equal to the negative of the partial derivative of w with respect to x. Now, the negative partial derivative of w with respect to x is going to be a positive mz over ei, and then it's going to be a minus partial of f1, which is a function of x and y with respect to x. If we integrate this equation with respect to z, we're going to get, starting with the far right term, a 1/2 m z squared over ei minus, now since f1 is only a function of x and y, its partial derivative will still just be a function of x and y at most, so that we can treat that as a constant when we integrate that. So it would be that term times z, but we could also potentially have a second function of x and y. Alright, now we're going to go back and look at, let's try this color. We're going to go back and look at this equation again. And we're going to take the partial derivative of that equation with respect to y. Okay, that first term goes away, and then we have the partial derivative of f1, which is a function of x and y, with respect to y. Let me make a little bit of room. All right. Now let's look at equation F. Now equation F says that the partial derivative of v with respect to z is equal to the negative of the partial derivative of w with respect to y. And we just found that, so that's equal minus the partial derivative of f1, which is a function of x and y with respect to y. So now we can integrate that. And we can find then that v, when we integrate with respect to z, is equal to minus partial derivative of f1, which is a function of x and y, with respect to y, times z, plus potentially a function of x and y. Alright, so I'm going to remove some of this information to make room for some other items here. So I have my u, v, and w equations so far over on the right hand side, and I think it's going to be safe now to remove these other lines. Let me just take another save of it right here. I want to leave the strain displacement equations, and I'm going to get rid of these equations right here. Alright, I'm going to label some things as well. I'm going to label this U equation, equation 1, and this V equation, equation 2. Alright, now let's take a look at equation A. Epsilon x is equal to the partial derivative of u with respect to x. Alright, now we have an expression for u, and so when we take the partial derivative of that with respect to x, the first term just goes away because it's not a function at all of x. We have the second term, which is going to be a minus z, and now we're going to have the second partial derivative of f1, which is a function of x and y, with respect to x twice, and that's going to be added to that partial derivative of f2, which is a function of x and y, with respect to x. And we also know that the strain is equal to, in the x direction, is equal to nu m times x over EI. Let me check that. I think that's supposed to be a z over EI. No, that's right. Nu m times x over EI. X is the direction that goes up and down in the beam. Again, I'm kind of used to using the formula sigma is equal to my over EI, but our coordinate system has been rotated. Now it's mx over EI for that strain. So our strain due to Poisson contraction in the x direction is Poisson's ratio nu times mx over EI. Alright, so that comes from equation 1. Right. Now we're going to take a look at equation B in a little bit more detail. Equation B says that epsilon y is equal to the partial derivative of v with respect to y. And now we're going to use equation 2 over here, and that would be the negative. We have the z multiplying by that, the negative of the second partial of f1, which is a function of x and y, with respect to y twice, plus the partial derivative of f3, which is a function of x and y, with respect to y, and we know that is also equal to nu m x over EI. And that simply comes from the partial derivative of 2 with respect to y. Okay, now if we look at this carefully, I'll try to use a different color. If we look at this carefully, on the left-hand side of this equation we have a z, and on the right-hand side we have an x. Okay, over here we've got a z, and over here we've got an x. Well, what that means is that that something can't be. All right. Now we know the right-hand sides of those equations have to be true. So what that means is, by equating coefficients, that the second partial derivative of f1 with respect to x and y of x and y with respect to x twice has to be equal to 0. And by the same reasoning, the second partial derivative of f1 with respect to x and y, of x and y with respect to y twice, also has to be equal to 0. And if that's the case, then we're left with these two things being equal to one another. And so we can integrate that equation with respect to x. So if we integrate that with respect to x, we're going to get a new mx squared over 2ei. And since this is a partial differential equation, we could have a function of y. This one here is actually a 3. Sorry about that. Comes from right here. And no, it's not. It's the second partial. Comes from this one right here. But what we can also say then is that since the second partial of f1 with respect to y twice is equal to 0, then we can set these two equal to 0. And by the same reasoning, the function f3, which is a function of x and y, if we integrate that with respect to y, we're going to get new mxy over ei. And we could have a function of x. Call that g2 of x. Now the last thing that we can do is we can take a look at these two partial derivative solutions, and f1 would have a solution that could be at most axy plus bx plus cy plus e. Alright, so we're chipping away at it. I think we have at least one equation that we haven't used yet. That would be equation D. For equation D, we've got the partial derivative of v with respect to x plus the partial derivative of u with respect to y is equal to 0. So let's look at the partial derivative of v with respect to x. And we're going to look at equation 2 again. We're going to come back over here and look at equation 2. We're going to have a minus z. We're going to have the second partial derivative of f1, which is a function of x and y, with respect to x and y. We're going to have partial derivative of f3, function of x and y, with respect to x. And then that is going to be equal to the negative of the partial derivative of u with respect to y. Okay, so now we're going to go to equation 1, and we're going to take the partial derivative of this with respect to y. And let's see what we've got here. We get no contribution from the first term. Okay, there's no x in there. In the second term, let's see what we get here. Before I get my signals crossed, let me pause this for a second. Oh, yeah, I got a little bit ahead of myself. So we have a functional expression for f1 and f3, so we're going to go ahead and use them at this point. So we've got a minus z. We'll use d in just a second, but we have an expression for f1. If we take the first partial derivative of that with respect to x and the second partial with respect to y, what we're going to have left, all we're going to have left with is a. Alright, so that comes from this term right here. Now we're going to have the partial derivative of f3 with respect to x and y. F3 with respect to x. Now f3 with respect to x is going to give us a plus nu my over ei. And since this is only a function of x, now we can get this down to a straight derivative of g2, which is a function of x, dx. Alright. Now we're going to do something similar for partial derivative of u with respect to y. Now we're going to go back and use equation 1, partial derivative of u with respect to y. We do get no contribution from the z squared term. And then we're going to have the second partial derivative of f1 with respect to x and y. So this is going to be a minus z, second partial derivative of f1 with respect to x and y, plus the partial derivative of f2, which is a function of x and y, with respect to y. Okay, so I'm just taking this u and I'm taking the partial derivative of that with respect to y. Now we know what these functions are. A function for f1, if we take the mixed partial derivative, the most that we can get is a. So that also has a term that looks like minus za. And then the partial derivative of f2 with respect to y, well, that term here goes away, and then we're going to have a straight derivative of function g1, which is a function of y, dy. Right now we can use equation d. So we're going to start off with the partial derivative of v with respect to x. It's equal plus partial of u with respect to y. Let's go ahead and write all those down. So we're going to have a minus za plus nu my over ei plus derivative of 2 with respect to x, and then we're going to have a minus za plus the derivative of g1 with respect to y equal to 0. Alright, and with that, I want to put all the z terms on one side and everything else on the other side. So let me write it this way. dg1 dy plus dg2 dx plus nu my over ei is equal to 2 az. Now by equating coefficients, the a term has to be equal to 0. Now if we know the A term is equal to 0, then we can separate these things out one more time. We can get the functions of y on one side, so that's like dg1 dy, and nu my over ei, and that would be equal to minus dg2 over by dx. Now we have a function of y over on the left hand side, and we've got something over on the right hand side that is not at all a function of y. So the best that we can have, the highest order that we can have, is that this is equal to a constant. Okay, so if dg2 by dx is equal to minus alpha, if we integrate that, now this is a straight derivative now, if we integrate that, then the function for g2 is going to be equal to minus alpha x plus another constant of integration beta. And if we rearrange this and solve for g1, then the best that g1 can be would be equal to minus nu my squared over ei plus an alpha y plus another constant of integration gamma. We now have enough information to write down expressions for u, v, and w. Okay, take a look at this page, maybe even print it out, and we're going to write down what we've got. All right, so putting it all together, we have these expressions for the displacement components u, v, and w. Now remember, the vertical displacement is the up and down displacement is the x displacement u. We have some displacements down the axis of the beam, that's the w, and we have some displacements in the cross-section dimension, v, that is in the y direction. Might be helpful if we sketched our coordinate system again. Yeah, so this is z, this was x, and when we looked at the cross-section, this was x and this is y. Now, this is kind of interesting. We can see that the displacement in the x direction is dependent on Poisson's ratio and where we are on the cross-section of the beam. You might remember from basic mechanics materials that like the top half of the beam in this case is going to be in tension and the bottom half of the beam is going to be in compression. X's could be both positive and negative. So you're going to get a positive contribution from the Poisson ratio term in some parts of it. You're going to get a negative contribution from the Poisson's ratio term in other parts of it. Now what we can do is we can fix the left end. And we can simplify this down. A lot of these terms, as we saw in the previous example, these coefficients will go to 0. Still get a complicated looking set of displacements. We have u is equal to m over 2ei, z squared plus nu x squared minus nu y squared. we get V, the V displacement term is equal to m over EI times nu xy, and we get the W displacement term to be minus m over EI times xz. Now we can talk about the plane formed by x is equal to 0. See if I can sketch this in 3 dimensions. Let's just leave it at that. The plane of x is equal to 0 in the dimensions of the cross section. Now when x is equal to 0, there's no v in w displacement. And that is called the neutral surface. That would be the plane of strain is equal to 0. Now we can go through and we can also take a look at the displacement fields that result from this. For fixed on the left hand side, the beam would kind of curve over like this. This line would be the displaced neutral axis. The neutral axis is the side view of the neutral surface. So NA for neutral axis. And we can compute the curvature of this beam as well. I'll write that down in a moment. But interestingly, the rectangular cross-section kind of changes its look as well. It takes a shape that kind of looks like this. And there is a radius of curvature associated with this direction as well. And it turns out that radius curvature depends on Poisson's ratio. All right, let me finally write down the expression for the radius of curvature. If we use a substitution of variables here, when we're on the neutral axis, we'll call that xi is equal to mz squared over 2e I. Then 1 over the radius of curvature is going to be equal to second derivative of xi with respect to eta. I need to draw better eta. Twice divided by 1 plus first derivative of xi with respect to eta squared all to the 3/2 power. Which, if we have small deformations, this derivative is very small. When we square it, it's even smaller. Add it to 1, it's pretty much 1. Take it to 3/2 powers, it's pretty much 1. So that gives us back the second derivative of xi with respect to eta twice, which is our typical expression for what we've got for 1 over r is equal to m over EI, which forms the basis of Bernoulli-Euler beam theory. needed to find my eta term. It would be like the z dimension. Alright, so we do get back all the things that we have in our elementary mechanics material solution, but by going through all of this extra math, we also have a lot more than what we have from our basic mechanics of material solutions. We get the displacement fields in all three different directions.